Hi, my name is Barak Sultanian. People know me by Becky. I'm VP of R&D in Sanborn mapping company, and I'm helping the company to transition from the very traditional way of doing stuff to get to the era of automation. Mostly we are dealing with the map, HD map, and all of these things.
And what kind of technology you use?
AI mostly.
AI?
Yeah.
Great. And you?
Hi, I'm Shamir Mirza. I'm the director of the R&D division for 7-Eleven, 7Next, and also the head of IT strategy. My background is in computer vision. We led the development of our in-store frictionless checkout technology where customers can use a QR code to scan in or track throughout the store, see exactly what they pick up and check out. Our IoT platform, as well as a self-service computer vision-based kiosk.
So before we start, I have a question because I never thought 7-Eleven runs in the R&D. So you guys have a big team or you have a big projects working on?
Yeah, so we actually...
One more question.
Yeah.
Have you launched any of those projects to your stores?
Yeah, actually.
Right.
So a couple of things. We have a team of about 60 people, a mix of hardware engineers, computer vision engineers, machine learning engineers. And our headquarters are in Dallas, Texas, Irving, Texas, actually. And we have a whole separate building, makerspace, labs, full mock store setup where we can test everything. Our Cashierla store is actually open at our headquarters right now for our store associates, customers, everyone who works at the store support center. We're launching it later this year for a public-facing store. And then we just put our computer vision test pilot for the self-checkout kiosk. That's going in at the end of this month. And our IoT platform is in 50 stores.
Right on. Great. All right, so I have a few questions for you. Feel free to answer whichever you feel comfortable. The first one is, for all of us who've been in AI and ML industry, so we've always been struggling to just find or choose the right model for the right task in terms of their accuracy and speed. So how do you manage this in your company?
This is a really important part of the AI. I mean, there are lots of research going on, and as some people call it, maybe noisy. But when it comes to the production, it's really important to choose the right ML. You cannot just pick something, whatever people, for example, they found in the first search. That's not probably the best one. So, for example, I will give you a couple of examples about for autonomous driving. When the car is in highway, average speed is 75 miles per hour. You need to have a model that detects fast, very fast, and at the same time having high accuracy. Mostly this is not gonna happen in one model. So what we did in my previous place is to mix match one high accuracy and then using something fast like YOLO family, any of the, its version could work perfectly in this case. So this is really important to know that if you choose a heavy model, this happened before, for example, someone came that I'm going to use RetinaNet, then I deployed on, transfer it to a platform like AWS, and then prune it, beaten up the accuracy out of that to compete with YOLO. So the question is why we should do that. This is a lot of time, and you can keep the RetinaNet for the accuracy and beautiful performance that it has, and then choose something lower accuracy but with a high speed. So this is really important when you're choosing your model. Think about the use case that you have. In another case we had, for example, it was offline processing of the images. And then here, the accuracy was the main, the important criteria for us. But someone came that we can use YOLO because it's fast, but it wasn't our problem. I mean, we could afford even a couple of minutes to get the result, but we needed with the high accuracy. So this is really important. But for example, in the second case, it's the thing is that you will get the lousy detection, and then somebody should sit manually, check everything, and then it's time-consuming work. But in the first place, I mean, the first case when you are in highway and you have autonomous driving car that could, cause catastrophe and end up with a collision or something like that, that's not something that you can afford it.
So from a retail perspective, my philosophy has always been use the dumbest thing that works. Just go with whatever's fastest. We'll try classical computer vision almost every time as the first approach. And if that doesn't give us the accuracy or speed we need, that's when we start looking at deep learning models and different ways of approaching recognition or classification. In actual practical application, what we found is, we did try going down the FPGA route and doing quantization of models and really focusing, but there's a tremendous loss in flexibility when you do that, right? And so the ability to be able to launch models and test different models out quickly is pretty key. So we've leveraged GPUs and edge compute within, that sort of paradigm. For us, consistently, testing the models and changing them out frequently is probably the most important thing. And when it comes to customer friction, people are really impatient, right? Like, you've been at a self-checkout kiosk and you're flipping through all the Apple types and all the Onion types or whatever else, and you're frustrated. You're like, wow, this sucks. And so how can we improve on that ability? And sometimes it's less, hey, we're gonna show you exactly the type of onion you have, but instead, here's 4 onions to choose from, right? If you're at the grocery store, for us, it's 4 types of taquitos. But you get the idea, right? It doesn't have to be the exact right answer. It just has to be faster and less friction.
That was a good segue when you touch on deep learning. Based on my own experience, most of the time, deep learning is a solution, but sometimes it's not. And how do you manage that? Choosing between deep learning and other options that you have. So any of you, please.
For me, it gets back to the application. For example, in some cases we needed to segment the images to mask, for example, part of the sky that was meddling with another algorithm that we were using for SLAM, for example. And the engineering come up with the solution that we are going to, use one of those RCNN for sort of segmentation. It's not only slow, but also very heavy, one of the heaviest, for example, models. So the solution that we came up with that we cannot afford a couple of neural networks running together in a, then we need a really large and powerful let's say, hardware platform to deploy those stuff. So we come up that, okay, for this part, we could just go with the traditional or conventional computer vision approach for segmenting the image and then remove, for example, or mask the sky. This is, again, I think it comes again to the application. As you mentioned, it's the speed and also the accuracy needed, and also another factor that's play a big role in that. For example, in autonomous driving applications, it's the hardware platform. The higher is the number of model that you're going to deploy on the hardware, then you have to have a supercomputer. The supercomputer needs the power supply. You need a power station attached to that, with the trailer, and then that needs the handling the thermal situation and everything. It becomes really complicated. So the first thing, as you said, try to think of the dumbest thing that can work, and then if it wasn't satisfactory, start to fine-tune that, and then at the end, you may end up to the point and say, okay, I can the only way to get that high accuracy and everything is deep neural network, then you have to think about that one too.
You, Shamir?
So I think any application of deep learning requires you to have a very firm understanding of, okay, what is the accuracy that I need? Is it absolutely critical? What is the cost I'm willing to take on to actually apply this? And then what is the effect of maintaining these models? Like what is the cost of maintaining the model? And for us, when thinking about putting things into production, retraining becomes a very large burden over time, right? Products constantly change out. When you're talking about product catalogs, what are methods that you could use that will allow you to narrow down the time you spend retraining? And so you're better off using stable architectures a lot of times that are well studied and using methods like contrastive loss as opposed to completely retraining from scratch. And then the actual burden comes down to how do you reduce the search space when you have a vector that comes out of that neural network and say, look, I have all of these things I can match against. How do I increase the speed of the lookup for that vector? And then how do I increase the probability that I'm selecting the right product, embedding from the database that I have?
Great, great. So let me ask this question, which is my last question, and then I'll let you ask your questions, okay? So we're gonna have enough time. So the last question I have is, it happened to all of data scientists or computer vision scientists. They make a model, for example, to detect a seed, and it works in this environment, but when you deploy somewhere else, it doesn't detect it properly. And that's how you generalize your model to work in any environment to detect any type of seeds. So have you encountered these type of problems, or
Absolutely, yeah.
if you do, how you tackle and solve it?
So there's a lot of classical approaches with deep learning, at least with image augmentation that a lot of folks use. One thing that we've actually done is also use synthetic data, so generating large amounts of synthetic data, 3D generated synthetic images across a variety of backgrounds and a variety of spaces and lighting conditions. And then the third thing, if you guys are familiar, there's a great paper, Copy, Paste, Learn, that you can take segmented images and then paste them into random backgrounds and try to extend the generalizability of your models to both extract what the information you need is, but apply to a variety of different random noise and background conditions. And so those three methods probably have been most effective for us in helping us generalize our models. And then the third thing is whenever you can, constrain the actual physical environment the best way possible. So for the kiosk, having consistent lighting, having the right camera angles, all those be fixed, because you can't reduce search space by knowing when someone was picking up an item. You only know when they're right there. For the store, you kind of have a inherent search space reduction because they're only interacting with a physical area in the store. So unless an item was previously misplaced, your search space is only the items in that area. And so your probability of selecting the right item is much higher because of that inherent search space reduction from physically moving in the store and tracking them.
Any input from you?
This is for, I agree with Shamir, that's for the time that you have to control in the environment. You can, when it's a store or something. But it happens in my previous life that we implemented a face recognition for for an OEM. And the problem with that was that we used one of those dataset, open source dataset, the original paper claim it's gonna be over 90 something accuracy, and then when we retrain it by ourselves and then try it, test, everything was beautiful, everything on the paper was, we could replicate approximately, and then we put it in front of the company to detect people's face, and we realized that our own model turned out to be a racist, doesn't recognize Canadian, didn't recognize the people from East Asia. It started to just white people, and even didn't recognize me. So it becomes a problem, and then we had to we cannot have a global, a unified lots of data from the whole world to train our model to recognize everybody's face. One thing that we had to sit with the business and also the program management and everything, to talk that what is the target. We figure out what is the country or the continent that we are going to deploy that first. So we started to, getting data from that area, 1 million, over 1 million data for the face recognition from a particular place, and then retrain it again. And then at that time, majority of the problem for people of that area was solved. It was recognizing perfectly, but our plan was for when we, for example, let's say deploy the car in another continent, another country, then we had to acquire another set of data and then make it happen, and gradually, extend our work work for the places that the business was.
Yeah, definitely biases in ML is a big topic. There's a number of papers recently released. Yeah, that's a great point. All right, so you ran out of my questions. Now it's your turn. You please. And then your second.
Hi, so thank you for the questions and the answers. In the case of the face detection that you just mentioned, as you said, you tried to train a separate model based on the different region that the model was supposed to be deployed. I was wondering after a while, when you had gathered new training data from these different regions, were you able to merge all of these models into one that can distinguish all of them? Or you kept it separate for each one of the regions in the production for the long term?
We kept it separate for two reasons. For example, a couple of million data set just start for retraining again. It was, at that point, having a platform to do that, a couple of years ago, it was a little bit challenge for us. The second thing that we thought that probably transfer learning will help, with a smaller set and then do that. That part we tested, it was okay, but still not as generalized as we wanted. So we stick to the first plan that for each continent or for each country, we would fine tune it for the people of that place. So because the case was in the situation that, for example, it wasn't the car, for example, we wanted to launch it in let's say, in East Asia, the likelihood of that car ending up in, let's say, in Canada was really low. So we skipped that part to have the general. But there were some approaches that we thought about, but because of the practicality and the timing, we stick to that different origin, different country or different area with different model trained on that data. Sure.
Yeah, hi. Great points there. Quick question about human resources and time. Given a production model, what do your engineers do for most of the time on those models? Like production model, what do your algorithm scientists spend their time doing on those models?
Once they're actually out.
Yeah, what do they do on a day-to-day basis on
Yeah.
production model? Like models have already gone into production.
So you're really monitoring for staleness and tracking accuracy over time. So a good example is for like the self-checkout kiosk. The failure mode is someone actually scans the barcode if it doesn't recognize it visually, right? And so you start looking at the rate of how frequently that's happening, how many customers are doing that, and monitoring the average time of transaction. Now, the best way to train those models, because there are so many different types of products across different types of stores and regions, is you kind of have to extract data off of those failed cases and aggregate it centrally. So a lot of that time is spent saying, okay, what were the failed cases? How did that model fail specifically when we map it in with t-SNE or UMAP and see visually the failure modes? Are they common? What's actually explainable about the failure modes? And then use that to do some level of transfer learning or additional model refinement to improve performance.
Any other questions?
Oh.
Okay. You're next. You're next.
I was curious about your guiding principles in deciding and choosing hardware platforms for running these algorithms. In computer vision,
I heard most of it. So the question is our guiding principles for choosing the hardware platforms for running the deep learning
Yeah,
models?
so I guess, I mean, there are different aspects, right? I mean, you said, oh, we want to pick the dumbest algorithm that works, which also implies that, you don't need a very powerful supercomputer or something to run it, right? I mean, there's cost implications, power consumption implications. There's a lot of security and privacy issues. I mean, you're doing computer vision, recognizing people's faces and whatnot. So I guess my general question is, do you prefer to run these things on private clouds or just enterprise servers, not even a cloud, or on the edge? I mean, generally speaking, okay, what kind of hardware platforms do you choose, and what are the, I guess, different,
This
guiding
is a
principles?
great question.
Yeah.
I don't want to take that question.
We can share.
Yeah, I can-
both
yeah.
of us. I will start. For example, again, I'm emphasizing on the the use case that you have. For example, for autonomous driving, the car is on the road, and the connectivity is one of the biggest issues. So if you want to deploy your model on cloud, you should have a sustainable connectivity, which is up to this point, it's one of the issues that everybody in OEMs just struggling with that. So the thing is, then it should be built in your car, in the car that you're going to launch it somewhere. So it can be the best. I mean, in majority of the companies that they're using, it's those edge devices from, for example, NVIDIA. They have some of the device, and also I heard that Qualcomm also working on a platform for this purpose. Then it comes to, for example, other cases for the face recognition. We could have, because the car mostly, when we were using that for example, to unlock something, the car mostly was in a garage, and probably there were the connectivity, sustainable connectivity most of the time. We could have a hybrid or hybrid approach that it could work on the the hardware inside the car, and also it could work on the cloud. So these are the way, I mean, how to choose. I mean, for me at least, in the use cases that I faced, was how to choose them in based on the use case that I have been involved. Probably there are cases that completely you can deploy everything on the cloud. So probably Shami, you
Yeah, I
can
think
continue.
for 7-Eleven,
Yeah,
this is very vital.
it's absolutely essential. So first, I want to make very clear, we don't use any facial recognition. We don't collect any biometric data. Even in our completely frictionless checkout store, it's a completely anonymized session with no facial recognition.
But let me
From
interrupt you.
security
No matter what you do,
Yeah.
as long as there's a camera,
Yeah.
people get nervous.
Absolutely.
How do you manage that?
Yeah, so first, from a security perspective, everything's on our own private cloud that does go to the cloud. Of that, we're actually only transferring metadata. So locally, most of the compute for the frictionless checkout store is local lockdown, completely just communicating metadata to the cloud. Aside from that, every single USB port, every single network port, all of that's locked down. So the self-checkout kiosks, all of that, completely shut off. We actually have the specific VID of anything that's able to connect to it, and that specifically has to be approved. As far as the IoT platform, we actually use the Azure Sphere chip via Azure Guardians to transfer data. So basically, you know every single system that's authenticating to our network and back to our cloud and outside. So getting things through security itself is a bit of a process. I mean, so we launched our first frictionless checkout store at our headquarters in about 7 months. I worked from March to November. But taking it to production has taken an additional 2+ years, because the complexity of getting the security right, the networking right, the hardware right, everything just as it should be to protect our consumers and customers takes quite some time. So,
Cool. Yep.
My question is along the similar lines, especially we have so many heavy models currently available, and to adopt them into our current systems, we need more computation power. And so how do you deal with that? How do you adopt these heavy models? Let's say you have a transformer
Yeah.
models. and you wanted to run them on a very on an edge device, let's say. And how do you deal with the inference time, because it needs a lot of computation to do it on the edge, and it becomes very valuable if you can do it on the edge.
Yeah.
So how do you deal with that problem?
Well, I'll say as far as using more complex models, so BIT is a great example. Awesome model. Choosing when to use those models is a trade-off on, again, back to accuracy and inference time, right? So when we're thinking about running models on the edge, we're not running those heavier models. What we're doing is we're streaming data to a more central server for our frictionless checkout store that says, hey, the confidence that we got from this lower accuracy model typically is not quite high enough. We're not sure. So I want you to rerun these frames specifically with the heavier model in terms of inference. It's both important from a model deployment perspective from, hey, I need bigger hardware, so that cost goes up, but also from an energy consumption perspective. I mean, deep learning from an environmental perspective is very computationally expensive, and anywhere where you can reduce the amount of heat produced, energy consumed, you should, right? So that choice is a huge trade-off, and one that we take very seriously and send over only when we need to.
How using NVIDIA's Tensor products to reduce your model impacts the accuracy of the model? If you want to just load it and inference on edge as
so the precision goes down. What we've seen is when we do shrink models or compress models down, right, quantize them, the performance stays decent, but sometimes it's the reason you chose that model is because it was significantly better than the other model. And oftentimes going through that process of reducing model size defeats the purpose of having chosen the more accurate model. And you can just use something, that's faster to begin with anyway.
Great, thank you. Next question and last question.
Thank you, first of all. And probably the question is related to the previous one and addressed to Baharak. You mentioned using of pruned models. Actually, what kind of pruning did you use, and what hardware platform did you use for this?
Pruning was one of the alternatives that proposed, and I disagree on that. But there are several models, for example, several approaches that if you search in the, you can find them. I don't recall all of them. I myself try to stick to the rule that if you have to prune a model to beat it up, the performance will go down if you do that most of the time. So I stick to the rule that if I need to prune a model, I will seek to find something lighter, because that's not, the purpose of choosing in the first place. So I never used pruning myself, but one of the proposal was that I rejected in the first place.
What about you, Shami?
So for model pruning itself, what we found is when you go down paths of chunking off important parts of models or reducing model weights, you lose something critical because there's such little explainability in these architectures to begin with. We don't understand how they'll fail. So, you're talking about mission critical systems or systems that you have to understand the failure mode. We don't use these larger deep learning models where we need to be able to explain and help understand the failure modes. And so generally speaking, I don't go down the pruning path at all. We stick with either use a smaller model or use transfer learning to tune the larger model and just take the cost of speed.
Cool. So thank you very much for being part of this this chat.
Thank you.
And hope you all enjoyed. Big round of applause.
Thank you.